Hi everyone. Today we're going to be talking about Supplement A, which is on systems of equations. The first topic we're going to talk about in Supplement A is solving linear systems by graphing. So we'll start with just some definitions. So when we define a, we're going to start with a two variable linear system. So we say a system of two linear equations, also called a linear system, consists of two variables or two equations that relate the two variables x and y that can be written in the form here below. So we use a little curly bracket, and we have like ax plus by equals c, and then ex plus fy equals g. So these capital letters are coefficients, they're just constants, so those would be like regular old numbers, and the x and y are the variables. So what a solution to this system implies is any pair of xy that satisfies all the equations, in this case, both of the equations. So let's look at a specific example here. So let's say we have the equations 4x plus y is equal to 8 and 2x minus 3y is equal to 18. So I might ask, is 2, 0 a solution? Well, to do that, all we're going to do is we're going to plug 2, 0 into both equations. So when I plug 2, 0 into equation 1, I get that 8 is equal to 8. So that works out. However, if I plug 2, 0 into equation 2, I get 4 equals 18. That's not true. So we'd say no, that 2, 0 is not a solution to this system because it doesn't satisfy both equations. Now I might ask, is 3, negative 4 a solution? So here we'll do the same thing. So we have 4 times 3 plus negative 4 equal 8. So that's 12 minus 4 equals 8. That's true. And then if I try this in equation 2, I have 2 times 3 minus 3 times negative 4 should equal 18. So 6 plus 12 does indeed equal 18. And since 3, negative 4 satisfies that both equations, we say yes, it is a solution. Now the big question becomes, and the question we're really going to be addressing throughout most of this chapter, is how do you find these solutions? Well, one way to find a solution is through graphing. So one way is graphing. So if I wanted to graph these two equations, on the same axes, what I'm going to do is I'm going to rewrite them so that they are in slope-intercept form. So my first equation, all I need to do is subtract 4x from both sides to get it into slope-intercept form. For my second equation, I'm going to subtract 2x from both sides. But then I also have to divide both sides by -3. And then what I'm going to do is I'm going to graph these two equations. So I would make like a XY table for each one of these. So equation 1, and then an XY table for equation 2. And now I have the freedom to really kind of pick whatever I want for my x's, and then I'll find the corresponding y's. So maybe for the first point, I'm going to pick 0 for x, and if I plug that in up here, when I plug 0 in for x, I just get 8 for y. And then if I pick, say, 2 for x, I get 0 for y. Again, I plug 2 in here. 4 times 2 is -8. -8 plus 8 is 0. Okay. For the next one, so I'm going to get, again, I'm going to pick a value for x. Let's pick 0. So when I plug that in, I get -6. And then let's say we pick 9 for x. 2/3 times 9 is +6, and 6 minus 6 is 0. Again, I'm picking my x's, it seems like maybe in a weird way, but it doesn't really matter. Any 2 points will describe a line, so they don't have to be picked in any weird way. I just picked them the way I wanted to. Now what I'm going to do is I'm going to, I'm going to graph these points. Except I want that. Let's try this one more time. Okay. So there's an XY axis. So I need this to be really, if it's 10 by 10 should be good. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So the first point I'm going to graph is going to be 0, 8 here. And then I have 2, 0. So oh boy. Oh boy. When I draw my line through these, it's going to look maybe something like that. And then I'll change colors and do blue. So then I have -6. So 1, 2, 3, 4, 5. 6 is there. And then +9 is here. All through those. And what we're interested in here is the intersection of these points, which if I look up, looks to be about +3 and about -4. Now, what's the drawback here of doing this graphically? Well, neatness becomes a big one, right? If you don't draw a nice, neat XY axis, it's going to be really difficult to estimate the correct point for the intersection. Another difficulty is, what if the solution is actually like 2.99 -4. Is it going to be realistic to get that kind of accuracy from looking at something you've graphed yourself by hand? No, probably not. So, we're not going to hang on to this graphing process very long, but there is some other possibilities that can happen when solving a system that we do want to talk about, and graphing really gives us some a nice way to kind of visualize what can happen. So we are going to continue talking about graphing, but just in terms of like understanding what these solutions should be looking like, and not in terms of necessarily using this as our primary solving method. Okay? So if I look at the 3 possible situations when we solve, so there's 3 possible solution sets. The first is what we've seen above, when we get exactly 1 solution. And we've seen what this looks like. We just have, 1 line for each equation. They intersect at 1 point. And that's it. The next situation is when we have, let's give this a name, we have no solution. So what that's going to mean is that our 2 lines never cross, i.e. they're parallel. So if there's no place where they share a common xy, there's no xy that satisfies both equations. The last situation, I should give it a name before I draw the picture, is infinitely many solutions. I abbreviate this IMS because it occurs somewhat regularly, and that's a nice abbreviation for us. So like if we were doing this, this might be the line for one equation, and this might be the line for the other equation. Or really you just have the same line each time. So because a line contains infinitely many points, there's infinite many solutions, infinitely many intersections, but not every xy is a solution. So it's not like an all real number situation where everything is a solution. No. Most points would not be solutions. Like if I pick this point out here, that's not a solution to this system. The things that are solutions must be points on these lines. Okay. So we can use these observations that we've just made, and we can even ascertain whether things are one solution, infinitely many solution, or no solution before we even attempted to graph them. So let's look at an example here. So let's say we have the system 4x minus 3y equals 8, and 8x minus 6y is equal to 16. So the first thing I might try to do is to rewrite these so that I could graph them. So I'm going to put them into slope-intercept form. So I'll subtract 4x from both sides, and then divide both sides by -3. And then if I do the same thing here, so again, I'm going to subtract 8x from both sides, and then divide both sides by -6. When I take -8 and divide it by -6, that reduces down to +4/3. When I take 16 and divide it by -6, that reduces down to -8/3. And what we notice here is that these two equations are identical. That tells me that these are both representing the same line, which in turn tells me that this is infinitely many solutions. And there's really no need for me to graph. I can tell this without even graphing. Now you could confirm this by graphing. If you wanted to, say, type these into your calculator, you'd see that you'd be getting the exact same line. But you don't need to do that. Just looking at the equation alone will tell us that they are the same. They are the same line. And that's pretty handy. Alternatively, if you had, say, looked at the original equation, you might have noticed that if we called this one equation A and this one equation B, that equation B is really just 2 times equation A, that 4 is 2 times 4 is 8, 2 times -3 is -6, and 2 times 8 is 16. This would also imply that we have the situation where they're the same line and there are infinitely many solutions. You can do that without having to go through all the rigmarole of putting them into suppA form. But sometimes it's hard to see that going on there. So suppA form is definitely safer, but in the instance where you can tell one is just a scalar multiple of the other, where it's a an integer scale factor like that, it's easy. Let's look at another example. So 2x plus y is equal to 4. 8x plus 4y is equal to 4. So again, we'll start by just putting them into slope-intercept form. So I'll subtract 2x from this one. So there's that. And here, we're going to subtract 8x. And then we'll divide both sides by 4. And now if we look at these two equations, you notice that they are not identical. However, they do have the same slope. Hopefully you remember back from your geometry course, I know that was a long time ago, but lines that have the same slope but different y-intercepts are going to be parallel. And that tells us then that we have no solution. Okay. Alternatively, you might have noticed that if I look at just the left-hand side, again, if I call this equation A and equation B is 2 times equation A, right? 2 times 4 is 8, and then 1 times 4 is 4. However, if I try to extend that to the right-hand side, 4 times 4 is not 4. So like half of your equation is a scale factor of another. That would tell you again that it's no solution. Oops, that was a 4a. Excuse me. So noticing that, you could go right away and say that this is no solution. Although there's nothing wrong with what we did there before, just rearranging them to get them into slope-intercept form. We have one last question, one last example to do. Let's look at a story problem situation. Okay. And through the magic of editing, there's our story problem. You ride an express bus from the town center, from the center of town to your street. You have 2 payment options. Option A is to buy a monthly pass and pay $1 per ride. Option B is to pay $2.50 per ride, and the monthly pass costs $30. After how many rides will the total cost of the two options be the same? Okay, so let's write an equation here to describe the situation. So we have two things that can vary here, right? We have the cost, and we have the number of rides. So I'm going to call the total cost. I'm going to represent that with the letter T for total. And let's do C for cost. And then we'll use R for the number of rides. So in option A, we can buy a monthly pass for $30 and then pay $1 per ride. So here our total cost, we're going to have the $30 for the monthly pass plus $1 for each ride we take. So C is going to equal 30 plus 1R. For option 2, we just pay $2.50 per ride. So the cost is 2.5 times R. Okay, so let's go ahead and draw a graph for this. So I'll do equation 1, I'll do in red. So here I'm going to treat R as like my X coordinate and C as my Y coordinate, because I've kind of set them up that way as independent and dependent variables. So when R is 0, C is 30. And when R is 10, actually let's do something. So let's do 30. Then this is 60. And this one we'll do in blue. So R and C. Because I have a feeling it's going to be a lot of rides before they have the same cost here. So when R is 0, C is 0. And when R is 30, C is 75. So let's go ahead and plot this. So I'm going to go by tens. So again, R is my X and C is my Y. So maybe we'll just go by tens. So 10, 20, 30. 10, 20, 30, 40, 50. Made those too far apart. Try it again. 10, 20, 30, 40, 50, 60, 70, 80. And then 10, 20, 30. Okay. So I have 0 and 30. And then 30 and 60. And then the next one, I have 0 and 0, and then 30 and 75. Somewhere like there. And so here is my intersection. It looks like if I track that down, that's 20. And if I track that over, that looks like 50. But I'm not totally sure. That was a pretty rough looking sketch there. I didn't use a ruler or anything. How can I know that 20 and 50 is correct? Well, I can go back to my original system and try plugging them in. So 50 is equal to 30 plus 1 times 20. Well, yeah, that's true. And then 50 is equal to 2.5 times 20. Oh yeah, that's true. So we can say at 20 rides, now you might say then, how can I, is there another way to do this other than by hand? Because if I didn't get the right answer when I did my estimate, now I'm just kind of guessing and checking. Yeah, there's another way to try to go at this where we can be where neatness does not become so much of a factor. And we do this by using our calculator. So let me pause for a second, get that set up. Okay. So what we'll do is we're going to just plot these two things on our calculator. So I'm going to use y as my variable for c and x as my variable for r. So I'm just going to go to the y equals menu and do 30 plus x. I don't need to type the 1 in. And for equation 2, I'm going to do 2.5x. Now I'm probably going to need to set my window because look at what my crazy stuff my window was from the last thing I was doing. So if we look about at this, 0 is a good minimum for x because that's representing 0 rides. And we know that the answer that we're looking for is around 20, or even just using what we plotted here. Using 30 would be a good one, and we scale that by, I don't know, 5s or something is fine. The same thing with the y, so the y min should be 0. Y is representing c, the minimum cost you can have is $0. And our maximum went up to, say, 75, so let's just do that. And again, we'll go by 10s or something there. So there's our first equation. There's our second equation. Here's our intersection that we're interested in. We can find that specific intersection now with our calculator. So I'm going to press second and trace. And the command that I'm going to choose is going to be the intersect command. So I'm going to scroll down and select the intersect command. Now down at the bottom here, the calculator is asking you some questions. It just really needs to know a couple of things. It needs to know which two curves do we want to find the intersection of. Notice now our cursor's popped up and we're on this curve right here. So that's one of the two curves we want to have we're interested in. So I'll press enter. And now it says second curve, and you notice that my cursor is automatically toggled to the next curve on my y equals menu. And put a little plus sign here and marking that this is one of the curves that I chose. Since this is the other curve I want to find the intersection with, I'll press enter again. And then it says to make a guess. So I can move close to where I think that intersection is. But it doesn't really matter. The calculator will find it, presuming that it's in these situations where you have straight lines and there's only one intersection. The calculator will find it no matter what. If you had multiple intersections, though, there's a place where the guess really is going to matter. But you'll notice here it tells us that intersection is when the x-coordinate is 20 and the y-coordinate is 50, which is exactly what we found when we did things by hand. That should do it. You should now be able to do everything that you need for this first set of homework. So thank you and good luck.